All right, folks, so we're going to pick up yesterday's lesson right from where we left off. So a little reminder of our essential question, which we didn't get heavy into, was how do cross-sections relate to the base of a prism or a cylinder, or also some other shapes. So yesterday we spent some time talking about, well, what is a right prism exactly? And we focused on how these two planes are parallel, these two regions are congruent, and this line here that connects its corresponding point down here is perpendicular to the base. That's what makes it a right rectangular prism. Now, if you flip ahead a few pages, we talked about some cross sections, and we ended class here. We ended class with these 6 cross sections, and what we found is shapes don't have to necessarily look the same to have basically the same cross section. They could be tilted. They don't always have to be right, like this one here. They could be oblique or general, but they have the same cross section if you just think about, well, what base is repeated here? So you get a circle and a circle, a triangle and a triangle, a pentagon and a pentagon. Or actually, those are quadrilaterals. So if we move on from this, we're gonna skip this page here. Let's move on ahead of that. But let's get to this page here. Now these definitions are out of order. We're gonna take this one first. So the first one we want to look at is a general cone. So we start here with a plane. And you've probably seen what a cone is, but you may not know what a general cone is. We start here with a plane, and B is the region in the plane, and V is a point that's not in the plane. So V is up here. V is the thing we call the vertex. So B is the base, V is the vertex. So if you see figure 2 here, the cone with base B and vertex V is the union, that means the combination, of all the segments for all the points P and B. So in other words, it's just these lines all meeting at one single vertex at the top. So that's a general cone. Notice we are used to seeing that as a circle. So a general cone with a disc base, first blank there, would be called a circular cone. So that's the one you're used to seeing. And we can sketch an example here. The base in that case is a circle. There's the vertex. And so that would be known as a circular cone. Now sometimes a general cone could have a polygon no base, meaning its base is a polygon, and then that would be called a pyramid. So pyramids and circular cones are both two types of general cones, but they're different based on their bases. So let's look at the rectangular pyramid. A general cone whose vertex, next blank here, whose vertex lies on the perpendicular line to the base and passes through the center of the base is a right cone. Or a right pyramid if the base is a polygon again, or is polygonal. Okay, what does this mean? So here you have 2 pyramids, right? Here you have 2 pyramids. This would just be called a pyramid. It wouldn't be a right pyramid because notice how this line is not perfectly in the center here. But this one, figure 4 here, would be the right pyramid. It'd be the right pyramid because it's making that right angle. That's exactly in the middle of that base. So let's label those, make sure we know. Here's our vertex at the top. That's that V region. Here would be your right pyramid. And then over here would be your rectangular pyramid because the base is a rectangle, but not necessarily a right pyramid because it doesn't go up straight from the center. All right, so those are some more specifics about, now we're talking about cones. So we have the general cone. Here's the big idea. General cone here at the top. Some base with some vertex, all the lines leading to the same point. And then if the base is a circle, it's a circular cone, like you've seen a lot of times before. If the base is a polygon, it's a pyramid. And it could either be a rectangular pyramid, or if it's kind of perfectly balanced, you could almost think of it as, these are like isosceles triangles, that's a right pyramid. All right, so let's move on to the next page. Remember, if I'm going too fast, you can just pause me and rewind. That's the great thing about this. So let's turn the page. Okay, a couple more notes now. So if we take a look at this, this would be, again, a right pyramid. If you look at the triangular region AVB, so think about this two-dimensional space here. A, V, And I apologize, I know it's small on your screen, but AVP. This is an example of what we'd call a lateral face. Lateral face. It's basically just a two-dimensional shape that's pulled out from a pyramid. So you could also have something called a lateral edge. So the edges are just the lines we see from the base leading up to the vertex. So there's 4 of them in this case. Let's name them together. You've got AV is one lateral edge, BV, those are the first 2 we've seen highlighted, and then you've got segment CV, and finally segment DV. So 2 of those combined with AB can make a lateral face. Each of those would be called the lateral edge. Sometimes we find the lateral edge. Okay, now this is really where we're kind of getting to today. So we've talked a little bit about cross sections that are created by taking parallel slices, parallel cross sections here that have a relationship to the base, no matter what the base is, like you see up here. Now, if we think of a dilation in 3D, we know, number one, we know that dilations are going to create similarity. That's for sure. We're going to have similar shapes when we dilate something. So when we dilate something in 3D, we're making a cross section, and that cross section is always going to be similar to the base. So we're going to, again, be able to connect to some things we know about similarity based on this idea. All right, let's kind of let that marinate in our heads for a second, make sure we understand this idea of similarity, and then we'll move on. Okay, so we're on to the next page now, example 1. Now we're going to actually do some of the work. And I'm going to kind of walk you through the first problem, but I'm going to encourage you to stop this along the way and try these out before I show you how to do them. It'll make more sense, even if you don't get it right, if you try these out before you just watch me do it. So let's look at the first one. Example 1. In the following triangular pyramid, a plane passes through the pyramid so that it is parallel to the base and results in the cross-section ABC prime. So here's our cross-section. And the base that it's parallel to is going to be the base of the pyramid here that I'm highlighting in blue. All right, so we've got our cross-section, we've got our base. So we know automatically, we just saw on the last page, these 2 triangles are going to be similar to each other. And we're also given another piece of information. They told us the area of ABC. They said the area of ABC is 25 millimeters squared. So what they want to know is they want the area of ABC prime. Okay, we said on the last page, these 2 shapes are similar. So think back to what we learned about with the scaling principle of area. If we're going to make this smaller, we can calculate the area from the original area by taking the scale factor and squaring it. Remember that formula we used, which was the original area times the scale factor squared is going to equal the new area, whatever it is. Now, what's the scale factor here? If you look closely at the problem, the scale factor here is going to be represented by the fractional distance from the vertex. So here we've got that length is 3, and the total length is 5. So this triangle ABC prime is basically 3/5 of the way from the vertex. So the original area is 25. The scale factor we're going to just call 3/5. We're going to have to square that because the ratio is the scale factor squared. And that's going to give us the area of ABC prime. So let's put that here. Okay, now let's just work through the math. So remember, you do the squaring first. So we're going to say 25 times 9, 3 times 3, over 25 is going to give us the area we want. Okay, now you can multiply this out if you want to. You can think of this as over 1. So the area we want is going to be 25 times 9 on top, so that's 225, divided by 1 times 25 on the bottom, that's 25. So we're going to do 225 divided by 25. And that's going to give us 9. So 9 millimeters squared would equal the area of triangle ABC prime. And now let's ask ourselves, like we always do, is that a reasonable answer? Well, if that's 25 down here, and we're getting 3/5 of the size, we know we're going to get smaller. So that seems like a reasonable answer to me. Okay, here I'd like you to pause it, take a couple minutes, try out example 2, make sure you're reading it very closely, and remember, if you're stuck, set up the equation the same way we started right here. So let's pause it right here. All right, hopefully you've had a chance to try that one out. Now, if you found yourself doing the exact same thing as up here, you might have ended up with an area that was bigger than or smaller than the original. Now, you have to be clear about something here. They actually did something different on us here. They gave us the area of the similar shape. So we're still going to start with that same equation, area times r squared equals area prime, but now we know what the prime area is. We know the area of ABC prime is 28. And then the scale factor again here is going to be 12 over 18. And what we're finding here is the area of the original. So let's maybe just call that A. Let's call that A, the area of ABC. So we know automatically whatever our area is, it better be bigger than 28 because that represents the smaller area of the cross section. So we know it should be bigger than 28. Okay, let's do ourselves a favor. Let's simplify this fraction before we try to square it. So let's call it 2/3, divide both sides by 6, the top and the bottom, before we square it. And so the area which we're solving for, square the 2 and the 4, is going to equal 28. Okay, now, how do we get rid of this fraction? We want to get the A alone. How do we get rid of this fraction? Well, if you want to take it in 2 steps, you could divide by 4 and then multiply by 9. But I like doing both of those steps at once. So let's multiply by the reciprocal. So we're going to multiply by 9 over 4 on both sides. And so 9 divided by 9, it's going to cancel. 4 divided by 4 is also going to cancel. So you're left with just A on the left side of the equation. I'm going to finish it down here. And then you're going to end up with 28 times 9 on the top. So 28, if we get our calculators out, 28 times 9. And that's going to give you 252. And then divide it by 4, because it's 4 times 1 on the bottom. Put that in there. And your new area, the area of the base here, is going to be 63. And we're still talking millimeters here, so 63 millimeters squared. All right. Let's have you pause again here and go ahead and try the next couple on your own. Okay, I'm going to leave you to it here on example 1, but let's talk about a new kind of idea here in example 3. This is something called the general cone cross-section theorem. And this theorem says, let's read it closely, if two general cones have the same base area, so let's highlight these in the same color. Let's make them both green. So even though they're different shapes, they're telling us that these two areas are the same. B and C is the same. They have the same base area and the same height. So the same height meaning that distance is the same for both of them, the exact same. We can call that H. Then that means the cross sections for the general cones, as long as they're the same distance from the vertex, so as long as that distance is the same, they're going to have the same area. Kind of makes sense, doesn't it? So it doesn't matter if they're not the same shape, as long as we're talking about the same area and the same height, well, the cross sections areas have to equal each other here. So if you want to maybe write down here why you think this cross-section theorem holds true, this is an idea you're definitely going to see come up on your exit ticket. So make sure you understand what we're saying here. The key was we started off, these two areas were the same, the heights were the same, so therefore a cross-section, as long as it's coming at the exact same distance from the top, from the vertex, it's going to have the same area too. All right. Okay, on this next page here, you have 3 practice problems to practice this idea, or just the similar idea we've seen before, that this cross-section is going to be similar to the base. I'm going to let you work these out on your own, so go ahead and pause it here and work these 3 out on your own. Okay, I'm assuming you paused it, and I'm going to come back from pausing it here, and I'm just going to give you right now the answers that I got. And sure, you could just copy the answers, but that's not really going to help you get the answer right. So here the height is 4. Here the new area was 9 square units. And here the height was 6 centimeters. So this is a way for you to check your work after you tried those on your own. And then if you have questions about this, we can talk about them tomorrow. Okay, this next section, I'm actually going to ask you to pause this video here and go watch a different video, because there's a visual I want you to get from this that is easier to show you with another YouTube video. So I want you to go to tinyurl.com/axis rotation. So let's go to that website, and you're going to watch this 4-minute Khan Academy video, and it should show you how to rotate triangular regions around an axis. So pause this video, go to that website, that tinyurl, and then come on back. Okay, I'm assuming you're back. I'm assuming you watched the video. So kind of cool if you looked at that video that when we talked about before how we go from 3D back to 2D, this is kind of the reverse. This is how you get 3D shapes from two-dimensional shapes. So if you think about rotating this triangle around this axis, we're going to end up with a circle at the bottom. So we're going to end up with this cone that has a really wide radius. So if we draw it out, you might want to draw it out down here, you're going to have a really wide radius, double the length of that radius here, so a diameter, double the length of that radius, and then it's all going to meet at that point. Let's just try to continue this line down here. Let's just do that. So they're all going to meet right here at that point. So this will give you just a big cone, and it's a cone that's kind of large. All right, and I'm not as good as Mr. Khan as drawing 3D shapes, but you can kind of get the idea here that this is going to give you a cone. Similarly, this is also going to give you a cone. It's just that the base is going to be a little bit skinnier. Now the base is going to be just about that much, and we'll go a little semicircle there, and then from that region here, we end up with our cone. Okay, and if you look at this, what you can kind of see is you could see the original triangle inside that cone. It's right there. If you took a cross section, that would be more of like a perpendicular cross section, but if you took that perpendicular cross section, you have that original triangle. Okay, so that's all we got. Take a look at this exit ticket. It should be in the homework pile. So you can take a look at this exit ticket.